Okay, so we're going to talk about high temperature superconductors. Now, before I start, let's talk about normal conductors. Right? So if you measure a normal metal, a copper wire at home, you get a resistance, and but the conductivity does change with temperature. So the question is the metal more conductive in winter or summer? Right? I guess everyone here probably know. So let me explain a little bit more. So here I'm plotting the temperature. So winter will have a lower temperature, summer has a higher temperature, so summer will be on the right side. And here we have electric resistance. So you think of the resistance as a tendency to fight against the conductivity. So more conductive means a lower resistance. So the real question is, are we talking about the A or B? If you think it's more conductive in the winter, then A has a lower temperature, is more conductive than it's A. If you think it's more conductive in the summer, then it's B. Right? So which one do we think, A or B? I'm going to count 1, 2, 3. Let's tell your answer. 1, 2, 3. A. Okay, great. Everyone got A on this quiz exam. So indeed, the answer is the resistance decreases as you decrease the temperature. So then the question is, what if we keep cooling down? Right? So the reason why the resistance decreases with temperature, you can think of electron running in a material like a kids running in the hallway. Right? So there are people in the hallway, it's not empty. Just like electron moving the lattice, there are atoms. So at a higher temperature, people are more energetic. They have parties, they dance, and they do everything. So it's harder for the kids to move through. Now at the lower temperature, people get quiet. They sit, they sleep, they even go home. So all of a sudden, the hallway becomes quieter. So it's easier for the kids to move through. The question is, what if we go to really low temperature? Let's say really low, absolute zero temperature. What's going to happen? Right? So this was a hard question, in the 19th century. So some people think, well, based on that analogous, at zero temperature, everyone frozen. So there's no activity at all in the hallway, so it's perfect for the kids to run through. It should have a zero resistance. But some people think, well, no, wait a second. Even if all the people are frozen, sometimes there's a desk left out, or there's a bump in the street. So you might have finite obstacles for the kids, therefore finite resistance. This was a question at the beginning of the 20th century. If you were a student back then in the physics department, this is one of the questions you wanted to answer. But these are theoretical hypotheses. To answer this question, you need experiment. Okay? So we have this brilliant scientist, Cameron Honest, and he was able to develop a technique to liquefy helium. This is not for fun. This is not for the liquid helium ice cream. This is for a real purpose. With this technique, he was able to get extremely low temperature. And then he tested this hypothesis. He cooled down a lot of metals and put it in and measure resistivity and see what happens. And in one of the metal that he cooled down, mercury. This is one of the very first fuel he cooled down. Mercury is a liquid at temperature, so he can purify very well, and he can handle easily. He cooled it down and measured resistance. And at high temperature, everything just like expected. But at low temperature, at some temperature, all of a sudden, the resistance disappeared. Right? This is different from this blue scenario, where the resistance gradually go to zero. In this case, this is more like a switch. At higher temperature, you switch it on, you have finite resistance. At certain temperature, all of a sudden, you flip it off, and it disappeared. This is totally unexpected. And this is called superconductivity, because there's no resistance. Conductivity really goes to infinite. Okay? But this happens at a very, very low temperature. Here is 4.2 K, and in terms of Fahrenheit, this is negative 400-ish Fahrenheit. Right? How cold is this? If you go out of the Earth, you go into the space, the temperature in the space is about 2.5 K. So this is only 2 degrees above the space temperature. This is extremely cold. So then, since the discovery, and one of the central goals in the physics is to bring this temperature a little bit higher. And ideally, we want your room temperature to be here, 65 Fahrenheit, so that even at room temperature, you have zero resistance. So the real question is, can we make this room temperature superconductor? But why would we even bother? Let me tell you one example. So globally, every year we generate 30 trillion kilowatt hour electricity. Now, that's a lot. But in order for us to use this electricity, it had to be transmitted from where it is generated to your home. And we use normal metal, like a copper wire, to transmit the electricity. And roughly 10% got lost during the transmission and distribution. 10% is average. If we do a long distance transmission, for example, people are talking about cover the entire Arizona, the desert there, with solar power, and then you can generate enough electricity and send to New York City, then that's a long distance transmission. You might lose up to 20%. So this is the average percent, but even 10%, that's 3 trillion kilowatt hour electricity. How much is this? This is 5 times of the usage in Germany every year. And that's roughly 3/4 of annual usage here in the United States. This is all because we use copper wire for the transmission. Imagine we have room temperature superconductor, then zero resistance. We don't lose anything upon transmission. We save a lot of energy here. Okay? That's not it. And there's a second thing we can imagine. So superconductor actually has 2 hallmarks. First is zero resistance. But second, it also repels magnetic field. So to demonstrate this, we actually have a demonstration. And I have let's get a volunteer. Why don't we have Zach? So let's do this demonstration. And here we actually have a superconductor. And we have a magnet track. We're going to demonstrate that this superconductor will actually flow on top of the superconductor, the magnet track. Okay? To start, this is at a room temperature now. So nothing will happen. This just stay on top. It does not float. We'll see what if we cool down to the superconducting transition temperature. Okay, is that map?
It is, but like just to pick it out of here.
Okay.
Want me to put it on the track or the?
Up to you. Okay. Now what we did, we cooled it down to its superconducting transition temperature. So now it becomes a superconductor. You can see that it flows on top. Not only that, it's not cold enough yet. You can actually flip it upside down. Not only it repels, it gets trapped there.
Let's see, good track work. There we go.
So if you really put on a track, it just moves freely.
There wasn't so much air in the room, it would go forever.
Yep, yeah. All right, thanks a lot. So with this, people can start to fantasize. We can envision something like this, a superconducting levitation train. Okay? Actually, this is not a fantasy. People are working on this. In Japan, they're building one. China is building one. And if you indeed have one of this, it's going to float 4 inches above the track. 4 inches is not very tall, it's this much. But that's enough to give you no friction and almost no maintenance is required. With this, you can reach 400 miles per hour speed. Right? If you drive on the highway, you get to 80 miles per hour, you get a speed ticket. But this gets to 400 miles per hour. And that's about 70% of the speed of an airline. So that's very, very close already. Basically, you have an airplane on the ground. Now, Japan and China are building one of this, but they're using the low temperature superconductors. So they have to be cooled down by liquid helium. That's a lot of energy. If we have a room temperature superconductor, then no energy cost. So the question is where we are. Are we getting there? Right? So the short answer is we're not there yet. Here I'm showing the roadmap for the superconductor. This x-axis is the time for the discovery. And the vertical axis is the temperature. And here is in Kelvin. So 0 Kelvin is absolute zero temperature. And the 300 Kelvin is about room temperature. So here at room temperature, we have nothing yet. But someone will say, wait a second. Look at this one. This one, lithium hydrides. This is not at room temperature, but this is 250. That's already warmer than the temperature in Antarctica. Even in summer. Okay? That's by definition, we have a room temperature superconductor there. Right? But don't be too excited. This needs pressure. We have to squeeze this material to get it into the superconducting temperature state. Well, you will say, well, it's not a big deal. Let's just squeeze it. But the pressure you required is this much, 170 GPa. How much is this? You need an elephant stand on a nail, and the pressure generated at the tip of the nail is about this much, on the order of this, but actually not there yet. You actually need 3 elephants sit on top of each other and to get this much pressure. So practically, this is not for the real application yet. So we're talking about ambient pressure room temperature superconductor. Then the highest TC is in this range is about 130-ish. Okay? So, however, 2 years ago, we almost got one. Almost. So what happened? Now 2 years ago, 2023, one day I woke up and I received a lot of messages. And people say, hey, please look at this paper. So some scientists from South Korea, and they reported the first room temperature ambient pressure superconductor. Okay? It's room temperature and ambient condition, no pressure required. The compound is copper, sulfur, lead, oxygen, very complicated. So they gave it a short name, LK99. LK are the last name initials of 2 of the authors. 99 is the year when they first saw the indication of superconductivity. So they have been working on this for 20 years. And in 23, they had enough evidence to show this is actually a superconductor. So what do they have? Here is resistance as a function of temperature, just like the very first plot we have. So you can see at high temperature, this is in Celsius. 100 Celsius is the boiling temperature of water. Right? Above that, you have finite resistance. And as you cool down, all of a sudden the resistance drops. This is not 0 yet, but if you keep cooling below 60 Celsius and below, it's almost 0 resistance. Now, keep in mind, superconductors have 2 hallmarks, 0 resistance and magnetic levitation. Here we go. They even show that this piece can float on top of a magnet. Wow, these are very solid evidence. Just in 10 days, a scientist from Lawrence Berkeley National Lab, one of the best national labs in the United States, he claimed that, well, I understand why this thing actually superconducts. Now, this gets the community really excited because these 2 Korean scientists was actually not very known. They did not have much record working on superconductivity, but here we have one scientist from one of the best national labs say that I understand why this thing superconducts. With this endorsement, you know what happened? The stock market, I guess people don't want to talk about this at the moment, but back then, 2 years ago, the stock price for those companies doing business on superconductors and just went so high in one day. In United States, there's one company. Their business is mainly on the energy-related thing. They don't do much thing about the superconductor, but their company name has superconductivity in there. Their stock price also went very high. And all of a sudden, if you go to YouTube, a lot of YouTubers teach you how you can make this LK99 right, at home. Well, that's going to be the energy solution tomorrow, so let's start. And my dad in China, he didn't know much about my research, but he knows that I work on superconductivity. So he was very concerned and called me and asked, are you going to lose your job? The fact that I'm still here tells you likely there's something else going on. So quickly, people realized it was not the material itself. There's some impurity in this material. And in this case, impurity is copper-2 sulfide. And this impurity, if you look at the resistance for this impurity state, it does look like a superconductor. At high temperature, resistance is finite, and drop seems like it go to 0. However, if you zoom in, if you plot on log scale, you can see there's a finite resistance. Not only that, the resistivity here is actually very, very high. This resistivity is 1,000 times higher than a copper. So this thing is actually almost an insulator. It just at a higher temperature, it's much, much more insulating. And it went through a phase transition, goes to a slightly less insulating state, but apparently it looks like a superconducting transition. This is what caused everything. Then you will ask, well, why can't it levitate? So it turns out the whole thing, the rest of the material is slightly ferromagnetic. Typically, a ferromagnet will stick to a magnet. But if the material is not uniform, some portion wants to attract to the magnet more than the other portion, then you can have a torque on the material. Then you can play with the material at some magic angle, at some position. You can have it like levitating. It's just a torque fighting the gravity. And that state is not stable. You can easily disturb and make it back. That's what they're showing in the picture. Okay? So now this time, theories come out again and say, we actually understand why this material does not superconduct. And at the same time, of course, the stock market price dropped. So this, once in a while, you will have stories like this. Right? So the bottom line is, we're still not there yet. You will ask, is it even possible to get to room temperature? If so, what's the secret? How do we get there? So let's look at what the real theorists say. We have a theory that came out in 1957, and they got a Nobel Prize in 1970s. It's called BCS theory. That's the last name initial of 3 of the authors. So what does this theory say? The theory says we have electron and positive ion inside of the material. Typically, electron hates the other electron. They have negative charge, and the electron will repel from another negative charge. But electron will attract the positive ion. Okay? So if one electron is here, this positive ion wants to move towards the negative electron. And therefore, locally, if you look at this area, you actually have more positive charge. Then another electron will feel, oh, there's more positive charge, I want to go to that area. So effectively, it's like this electron can talk to this electron. Actually, they have attraction between the two. The BCS theory also says, in order for this to happen, 2 electrons needs to have a so-called spin up and a spin down. Okay? So you have 2 electrons effectively form a pair. Well, in the material, you don't have only 2 electrons. You have many, many electrons. And every 2 form a pair. Eventually, you have a lot of such so-called Cooper pair. When you have this Cooper pair, they form a so-called condensate. They form a so-called coherent state. So what is this? Typically, an electron moves independently. It's just like you walk on the street randomly, and you bump to others, and it's very hard to move. But imagine all this, they form a coherent, consistent way. So it's like a marching band. Even if you have 10,000 people, if you feel an organized marching band, you can move freely without bumping into another person. That's how the superconductor moves. The electron moves in the superconductor. Okay, so coherent state, all the Cooper pairs move in a coherent, consistent way. If this theory is right, it tells us the Tc, the transition temperature, is related with 3 things. What are the 3 things? One, that lattice has to respond to the electron. Therefore, the lattice needs to vibrate. So we want higher frequency of vibration, and therefore you would like small mass. And also, you want a lot of free electrons. So we want a number of the free electrons. Therefore, the more free electrons you have, more likely you have a metal. And also, you want the electron to talk to that lattice. Right? So likely we want so-called covalent bonding. So what is this? For typical metal, the ion and ion interaction form a bonding, and you have electrons moving in a background freely. However, in a covalent bond, you have one atom contribute 1 electron, another atom contribute 1 electron. These 2 electrons will form a bonding, so the bonding itself is formed by the electron. Therefore, electron can affect the lattice. But if you have this, likely you have a non-metallic state. So we're fighting between a metallic and a non-metallic. The strategy is likely we can mix metal with non-metal, but you want lighter elements. So along that strategy, people thought about, for example, niobium nitride. Niobium is metal, nitrogen typically is non-metal, and nitrogen, the mass is small, so that fulfills the philosophy. And indeed, the Tc is 16K, much, much higher than the initial Tc. Okay? So the initial effort is really along this direction, and there's one person we want to mention. This is Bernd Matthias. Okay? So Matthias did his degree in Europe, and he grew up in Europe. And during the World War, he came to the United States, and he worked in Bell Lab, and eventually he became a professor in UC San Diego. Why this person is important? Him alone discovered about 1,000 superconductors. That's really, really amazing. Given that his career is probably like 40 years long, that tells us every year he discovered 20 to 30 superconductors. So each month he has to discover 2. That's a lot. Right? And so he is a single individual who discovered most superconductors in the world, in the history so far. And he discovered some of the very interesting, very important superconductors, like niobium titanium. This is a superconductor that has 90% of the market right now. And if you go to a hospital, if you do MRI, for example, MRI need a magnetic field, a strong magnetic field, and you need a superconductor to provide that field. Very likely you have niobium titanium, and the rest likely use magnesium diboride. So if you ever do an MRI, or if you in the future you will do MRI, you owe a big thanks to Matthias. Okay, so we want to ask how can he discover so many? He actually has his own rules to discover this. So these are called Matthias rule. So for example, he wants to look for high symmetry compound, for example, cubic, and based on BCS, he thinks a large density state that tells you more free electrons. He wants to stay away from oxygen, stay away from magnetism, stay away from insulators. But in my opinion, there's one more rule that he didn't say specifically. That is, try everything. He tried a lot. For example, in one of the single paper, search for new superconducting compound. Guess how many compounds were there in one single paper? 102 compounds in one paper. And he discovered 22 superconductors in that single paper. So nowadays, this will be 102 papers. Now, as we move into the next stage, the high Tc superconducting stage, turns out all these rules will get violated. But one rule on his list still remains relevant. That is, stay away from the theorists. Okay. Not only Matthias is a very good researcher, he discovered 1,000 superconductors, he's also a very, very good educator. And many of his students are contributed a lot to the research of superconductivity. For example, these are 3 of his students. And nowadays, the highest award for the field of superconductivity is named after his name, after him. So Matthias Prize. These are 3 of his students who received Matthias Prize for their contribution for superconductivity. Dr. Brian Maple, he is a professor at UCSD, and he's still working there. And he had a postdoc and who also works on superconductivity, and that is me. And Zach Fisk, he worked in Los Alamos National Lab for quite a long time, and then he became, before he got retired, he was a professor at UC Irvine. UC Irvine. He had a postdoc, Paul Canfield. This is one of the world-known expert on the superconductivity. He worked on, for example, iron-based superconductor, magnesium diboride, and a lot of others. And Paul Canfield had a PhD student who is also working on the superconductivity, and that is also me. So every time when I look at the picture, I feel very stressful, right? Discovered 1,000 superconductors, contribute significantly to the field. World-known expert, nobody yet. Okay, so now let's back to the roadmap again. So people searched for superconductivity under the guidance of BCI theory and Matthias rule, and for quite a long time, we were not able to get the TC above 40K. Actually, there was even a theory that says 40K is the limit. So why 40K is the limit, and why can't we get over this? That's really a mystery for the field. However, everything was changed, as you can see here. That's in 1986. So what happened in 1986? I was born. But more importantly, two scientists, so Carl Alex Mueller and Johannes Bernd, they were scientists in the IBM in Switzerland. And one thing is they were not expert on superconductivity at all. And before they discovered cuprate, they had no paper on superconductivity. However, Mueller was already the director of the division he worked in. And he is really an expert on material synthesis, and especially the oxides. He never worked on superconductivity, but he always wanted to work on superconductivity. And he had a theory how you can get to high TC superconductors. But that theory goes against the Matthias rule. Basically, he wanted to work on lanthanum nickel-based oxide, right? Matthias says, stay away from oxide. And this oxide is insulator, is close to magnetism, and it's not cubic. So this idea was considered as crazy. However, Johannes Bernd, he was a young postdoc, just joined his group. He had zero experience on superconductivity. So it's relatively easy to convince him this is actually a good idea. But this is not their main job. So they had to work on their main project, whatever funding agency is, right? So they had to work on that project during the weekdays. But Mueller was able to convince Johannes that, over the weekend, instead of going to those boring Saturday science event, or playing video game, or watching soccer game, you should come to the lab and work on this lanthanum nickel-based oxides. So they worked on this for a long time, for like 2 years-ish. They didn't get anything. Until one day, another group from France, they reported another oxide. Instead of nickel-based, they reported a copper-based oxides. And these were 3 authors, but I wasn't able to find a picture for these 2. Apparently, they're not very famous. But the last one, Bernard Raviel, he is actually a very famous crystal synthesized person. He worked a long time on oxides for functionality. But he was not interested in superconductivity. As a matter of fact, when he discovered this material, he went up the temperature, not go down. So here's the resistance as a function of temperature in Celsius. You can see he actually went up to boiling temperature of water and eventually go to 300 Celsius. He only cooled down slightly. So his main interest is higher temperature, not lower temperature. The interesting thing he found is this system supposed to be an oxide, supposed to be insulator. However, if you replace some of the lanthanum with barium, you can turn this into a metal. Right? This is the quiz problem we had at the beginning. A metal, the resistance will cool down, will decrease as you cool it down. This is typical behavior of metal. That's it of the study. However, when Mueller saw this, he was super excited. This is exactly what he was looking for. When he worked on lanthanum nickel-based oxide, he was thinking, if we take oxide, if somehow I can make it metallic, you can likely get superconductivity. So here we go. This is one. So he decided, all right, we should stop working on the nickel-based oxide. Let's move on to the copper-based oxide. And indeed, within a year, they found superconductivity. Here, resistance started to drop. At some low temperature, it goes to 0. Okay? The initial TC was 33K, not super high. However, this compound violates all the rules of Matthias. It's not cubic. It doesn't have high density electron. It's close to it's oxide, close to magnetism, close to insulator. So this really drives people crazy and made people really excited. However, if you look at the title, right, unlike compared to the other, what you call, we find the first room temperature superconductor, such a big discovery, they call it possible high TC superconductor. Right. The reason for the humble is because at the time, they did not have magnetic measurement. Remember the two hallmarks, zero resistance and the magnetic levitation. Right? The reason why they didn't have this is because they were not ready for this. They did not even have the equipment to finish the experiment. They only have equipment to measure resistance. When they saw this, they published and they placed order for the equipment. When the equipment arrived, they measured and they published the second paper. That's already the next year. And in the same year, they got a Nobel Prize. This is very, very rare. Typically, you make discovery and you get Nobel Prize in 30 years. And here, you make discovery in 1986, you got Nobel Prize 1987. Right? Because this is really one of the big discoveries. So initial TC was 33. Now people know where to look for. Right? All of a sudden, all over the world, scientists start jumping in and work on this. How do we possibly increase the TC further? Here's the periodic table, and the elements are here. You have barium, lanthanum, copper, oxide. At the time, people already thought copper and oxygen must be related to the superconductivity. Let's keep this intact. And we want to replace barium with something else, or replace lanthanum with something else, and see if we can make it better, or make it worse. That still is valuable information. Okay? So keep that in mind. In just a few months, Paul Chu, one of Matthias' students, and he took the same material, he applied pressure, he was able to drive it from 33K to 40K. At the same time, one group in US, Bob Kava, and another group in China, they published at the same time on the same compound, that is lanthanum strontium. So barium was here, now strontium is right above. So they replaced the barium with strontium, and they were able to get TC 36 and 48. The difference comes in how much you replace, the exact formula of the compound. Okay? Now, just within a month, this was January 1987, February 87, 3 groups, Paul Chu from US, a group in Japan, a group in China, in the same month, they report the same compound with roughly the same TC. So this time, they keep the barium same, they replace lanthanum with yttrium. So we have yttrium, barium, copper oxide. And by the way, that's exactly the superconductor we used for this demonstration. Okay? And interesting thing is, not only they published in the same time, on the same compound with same TC, they even published in the same manner. And now, if you have an exciting story, you write a paper, you put it on the archive online, and so that everyone will know. right? Because you are afraid of sending to the journal first. You send to the journal, get it reviewed. Who knows who the reviewers are? It might be your competitor. They might just reject your paper and do the experiment there by themselves, which is not legal, but people are afraid of doing this. So they were afraid of that might happen. Instead of submitting the paper to a journal, all the three groups held a press conference. They announced the news in front of reporters and get it published on the newspaper. Then they submitted in the journal. Even then, one of the group, when they submitted the paper, they intentionally put a wrong formula. So Y is yttrium. Yttrium's here. There's another element on the periodic table with a very similar symbol, YB, which is ytterbium, and that's also one of the rare earths. Okay, so instead of yttrium, they put ytterbium when they submit it. When the paper gets accepted, they said, oh, there was a typo in the formula. By the way, it's actually yttrium. I mean, that's understandable given that 40 years ago there was no internet. Right? It's very hard to really claim the credit for this. But this tells you how much the competition was at the time. So in the next few years, people were able to even more modify the formula, and eventually we get to 133K. So these are still very low temperature, but getting above liquid nitrogen temperature, getting to 93K, is actually significant. Because in this temperature range, you actually need liquid helium to cool it down, and the price is $30 a liter. Now in this range, you're above the liquid nitrogen temperature, and now you can cool it down with liquid nitrogen with 30 cents per liter. This is much, much cheaper. Right? For that reason, and YBCO now start putting the commercial use. Right? YBCO is actually very easy to make. Even though this sounds fancy, this is one of the biggest discoveries in the human history. The way you can make this is very, very simple. You just buy this powder, copper oxide, yttrium oxide, barium carbonate. Then you just mix the powder and use a press. You press it in your pellet, something like this. Then you just put it in the oven. You have to bake at a few hundred Celsius, a few hundred Kelvin, and within 2 or 3 days, you can get a superconductor. Right? When I was at UCSD as a postdoc, there was 2 theorists. They were eager to make YBCO, so they came down to the lab. 2 theorists, do exactly the same thing. They mix, they grind, they bake.
You let theorists in the lab?
We do. They have to do the safety training, though. Okay. The funny thing is, your 2 theorists do exactly the same thing, and one has slightly higher TC, so he feels like, what's wrong with this? Theoretically, they should be identical. However, this bulk material won't be very useful. In order for the real application, you have to make it a wire. This material is very hard to make a wire, so people make a tape instead. To make tape is much harder. You can't glue tape directly. You have to put tape on some bottom layer for protection. So you have to make the metal layer, then you make a buffer layer, and there are many steps for the buffer layer. Then you make the YBCO tape, then you make the protection layer. Right. This is already a simplified version. The real version, there are so many layers. Only one layer, this white one, is YBCO. All the others either for protection or is the buffer layer. Okay, so this is already real thing. It's not a fantasy anymore. So now you can buy with $20 to $100 per feet. The price is because it depends on how many you buy. If you buy a lot, you probably get a discount. It's on the lower end. If you buy only 1 feet, it's likely $200. Okay, and with this, there are a lot of applications now. We talk about the power transmission. We talk about the levitation train. But there's one major driving force for this. That's the nuclear fission. A few years ago, people achieved nuclear fission now. So the mission now is to scale it up, make it longer, make it bigger. But for that, you need a magnetic field to confine the nuclear fission. Right? So for this purpose, obviously you want a strong magnetic field. You want a higher temperature. So YBCO is perfect for this. So majority of this is actually for the nuclear fission. Right now, the superconducting market is 12 billion for last year, and is projected to go to 30 billion in 10 years. And right now, 10% is for YBCO. So that's actually a large business market already. For us, for the physicists, we want to understand why this happens. Right? So far, unfortunately, we do not have a theory to explain why this type of material can superconduct. So from material point of view, the question is, can we find another material instead of a copper? For next 20 years, people are looking for other systems similar to copper oxide and do the same thing. That happened 2008. Okay? So 2008, a group in Japan, Hosono's group, again, he's not an expert on superconductor at all. And he is known for the discovery of indium gallium zinc oxide, which is used for the screen of smartphone. So we're actually using this material every day. And that's his expertise, oxides and functional materials. But while he was working on that direction, accidentally they discovered this iron-based, iron arsenide lanthanum oxide, this family of material. So the initial TC was 26K, and this was already exciting enough, and people will think, well, just like a cuprate, maybe quickly we can increase the TC and eventually go about 100K. So at the time, all those superconducting labs are working on this, and I just started my PhD study there. So my entire PhD was on this family of a compound, but this family is much harder to work with because you have arsenic, right? Arsenic has high vapor pressure, explosive, and toxic. The worst combination you can have ever. So the first time I sealed 70 grams of iron arsenic, and get exploded the next day. Now, fortunately, that happened overnight, and no one was in the room, and the entire room was under ventilation, so it got sucked. I was freaked out when I heard that, but the senior student who worked with me, was very normal. He says, "No, don't worry," and that happens. I said, "Well, what about the arsenic? It's all gone. All contributed to the atmosphere of Ames." So for that reason, we have to do the safety check every year. We do the urine test every year. And I saw that my arsenic level actually increased every year. It's still well below the threshold, but it does increase. So by my prediction, I said, okay, I need to graduate. But anyway, people were able to get to 55K and in a year, actually. Now the highest TC is about 90K, but that's in the film and it's under strains, so it's not a normal condition. So we call the bulk material about 55K. This is still well below the liquid nitrogen temperature, but this family share a lot of similarity with the cuprate. So they're both layered structure. They're not good metal. They're close to insulator. They're close to magnetism. They have low symmetry. So all these things make people think this might answer the mechanism for this entire class of material. So now we have a new kind of rules to look for high TC superconductors. You want transition metals. You want layered structure. You want this to be close to magnetism. And you want it to be metallic but bad metal. You want like a niobium. You don't want niobium. You want close to insulator. And of course, you still stay away from the theorists. Okay? Now if you look at all these criteria, where do you find on the periodic table? So now we have copper, we have iron. Naturally, you want to ask, what about cobalt and nickel? Indeed, nickel forms a complex oxide. So just 2 years ago, one group in China, they discovered this family, lanthanum nickel oxide, and when they apply pressure, this turns into a superconductor. Again, this is not ambient pressure. You have to apply 20 GPa of pressure, Tc is about 60-ish K. Okay? And this compound shared a lot of similarity with cuprate and iron-based. So, but can we increase it further? Can we make it ambient pressure? These are still the active research right now. But one thing I want to point out, this material is actually the material that Mueller wanted to study before he studied cuprate in 1980s. And this material, exact material, was studied by John Goodenough, who got Nobel Prize for the lithium battery. He studied exactly this material in 1994. And he indeed measured conductivity. He did not find a superconductor because he didn't apply the pressure. He even suspected what are the reasons why this one did not superconduct. So sometimes...
Is that name a joke? Good enough?
Good enough? No, he got Nobel Prize. Okay. Yeah, that's a real name. Actually, I had the same question when I was a PhD student. One professor recommended a textbook on magnetism written by Goodenough. I said, was that a joke? Actually, now I have a copy of this book in my office. So doing research sometimes is like this. You're very, very close sometimes, but you don't know. This is the nature of the research. We're going into the unexplored territory. You don't know what's in front of you. No one can tell you. Sometimes when you look back, you say, wow, I was so close, but there's nothing you can do. And this happens for all types of research, and especially for the discovery of superconductivity. Before I finish, I have two more stories along that direction. One is about this manganese diboride, and this is a superconductor with 33 K of Tc, not very high, but the elements are cheap, and it's very easy to fabricate into wire so that there is already 15% of the superconducting market for this single compound. Okay? If you go to do MRI, if its magnet is not made from niobium titanium, likely is this material. Now, this material was discovered 2001 by Japanese scientist Jun Akimitsu. And Akimitsu announced this on a conference. Unlike those cuprate people who were very cautious, he just said, you know what, we're working on magnesium diboride, and it seems like it might superconduct. Wow, all of a sudden people are, what? What are you talking about? So in the audience, one of the people is my PhD advisor, Paul Canfield. When he heard this news, he immediately ran home and started experiment. So indeed, the two groups published the results on superconductivity roughly at the same time in March of 2001. Okay? This is not the main point of the story. The main point of the story is this compound was actually discovered 1954. So here is a way another way to detect superconductivity. You measure specific heat as a function of temperature. This is the data this is typo 2001 that shows you have a superconductivity. How do we know? This data smoothly increases as you increase the temperature until you hit here. There's a tiny kink. Right? Even though it's tiny, it's well visible. A well-trained physicist will tell there's something going on. Then you do some careful study, for example, resistance, you will find the superconductivity. The same data was measured in 1957. The blue data you can see is actually very similar to the red one, but the blue data does not have enough density to tell there's actually a kink. If this group spend a little bit more time, if spend 2 more days on this compound, they would have discovered superconductivity as early as 1957. Another story, in 2017, a young postdoc was working on a uranium compound. He used a so-called chemical vapor transport to make the material. He was aiming for this uranium-7 tellurium-12. And he spent weeks on this, and eventually he got nice crystals, but X-ray says this is not what you want. This is uranium tellurium-2 instead. Now, uranium tellurium-2 is actually very close to this. Right? This is basically uranium-7 tellurium-14, which is very close. But it's indeed a different compound. Now, this postdoc, desperate enough, he decided, let me just work on this instead. So first he did some literature search. Turns out this compound was already studied since 1967. And people already measured resistance. This is resistance as a function of temperature. You see a drop, but this is not superconducting. If you zoom in, you can see resistance does drop as you decrease the temperature, but this is going to go to a finite value. So he decided, well, let me just cool it down a little bit further. And indeed, it goes to 0. If you zoom in, you can see this was the data people already knew, about 2K. All he did, he cooled down a little bit further, and it became a superconductor. And this was reported on Science, and by the way, that person was me. Okay, so you would say, well, why would we even care? This is only 2K, it's even lower than the compound you showed at the very beginning. That was 4K. The thing is, for a superconductor, not only you have a critical temperature, there's also a so-called critical magnetic field. So if you apply too much magnetic field, superconductivity also gets killed. This is the room temperature or high temperature superconductivity under pressure, right? So transition temperature is about 200-ish. If you apply 60 Tesla of magnetic field, superconductivity gets killed. The superconductor that I discovered, even though the TC is only roughly 2, 100 times smaller, it can stand in magnetic field of 35 Tesla. If you scale this temperature by 100 times, then the critical field is 3,000 Tesla. This is extremely high for such low TC superconductor. And we figured out that's likely because this is actually a topological superconductor that might be useful for the quantum computing. Okay? So that's it about my talk. Towards the end, I just want to say, sorry, we don't have a room temperature superconductor yet. However, theory does not forbid this. It's not forbidden by any theoretical calculation. So we believe at some point, if we work really hard or work really smart, we'll get there. And my intuition is likely the answer is some complex compound, because all those simple ones have been extensively investigated in the past few decades, especially at higher temperature. If we look for room temperature superconductor, likely those ones will not be the one. And from all this story, we learned that you have to work outside the box. Nothing is impossible, but we need bold ideas. And I do think we need to stay close to the theorists. Because for us physicists, not only we want to find the material, we want to understand what's the mechanism of this high TC superconductor. For that purpose, we do need to work closely with theorists. Okay, with that, thanks for your attention.